Welcome to this session. Today, we'll tackle the problem number 130, surrounded regions. This problem is an excellent opportunity to deepen your understanding of graph traversal techniques like depth-first search, DFS, and breadth-first search, BFS. Get ready to learn and explore key problem-solving strategies. In this problem, we are tasked with processing a 2D grid, or board, containing characters X and O. The goal is to identify regions of O's that are completely surrounded by X's, and then flip all the O's in those regions to X. A region is considered surrounded if it is enclosed by X's on all four sides, including diagonally. This means that any O that touches the boundary of the board or is connected to another O that touches the boundary will not be flipped. The function we implement will modify the board directly, making these changes in place. Now, let's look at the input and output formats. The input is a 2D grid represented as a list of lists of characters, where each character is either X or O. The output is the same grid, but with the necessary flips applied. This will help us identify how the solution transforms the board to meet the problem requirements. Here is an example to clarify the task. Consider this 4x4 board where some cells contain X and others contain O. The output shows the board after the surrounded regions of O's have been flipped to X. Notice that the two O's in the second row and the single O in the third row are surrounded by X's on all sides. These O's are flipped to X. The explanation makes it clear that these transformations occur because those O's are fully enclosed, or surrounded, by X's. This demonstrates the core concept of the problem, identifying and flipping only those regions that meet the surrounded condition. Now, let's highlight the O in the fourth row. This particular O is not flipped because it is not completely surrounded. It touches the boundary of the board, and any O connected to the boundary directly or indirectly cannot be part of a surrounded region. This example also shows how the function handles boards with no changes required. For instance, in the second example, the board consists of just one cell, which is X. Since there are no O's present, the board remains unchanged. This demonstrates that the solution should handle such edge cases gracefully. Here's another example with a slightly larger 5x4 board that contains a mix of X and O. In the output, we see that the O's in the second row are flipped to X because they are surrounded by X's on all sides. On the other hand, the O's in the first and last rows, as well as those in the fourth column, remain unchanged. This is because they are either touching the boundary directly or are connected to an O that touches the boundary. This example highlights the importance of checking connectivity to the boundary when determining whether an O is part of a surrounded region. To summarize, the O's in the second row are flipped because they are surrounded, while the others remain unchanged due to their connection to the boundary. The constraints of the problem ensure that the board's dimensions are manageable, with both the number of rows and columns ranging from 1 to 200. This means we need an efficient solution that operates within these bounds. Additionally, the board only contains X and O, so no other characters need to be handled. Edge cases to consider include scenarios where the board is very small, contains only X, or has all O's connected to the boundary. These cases help us ensure that our solution works for all possible inputs, including the most extreme configurations. To start, let's consider the brute force approach. The intuition behind this method is to traverse every cell in the board and check each O to determine if it is part of a region completely surrounded by X. This is done using a helper function that performs a depth-first search or breadth-first search from each O to see if it touches a border. If it doesn't, all connected O's are marked as captured, converted to X. However, this approach has significant downsides. First, it involves a lot of repeated work, as the DFS or BFS is performed for every O, even if those regions have already been processed. Second, the time complexity is extremely high. In the worst case, it's O, open parenthesis m times n close parenthesis squared, due to redundant traversals of the board. This makes the brute force approach inefficient and impractical for larger boards. Now, let's explore an optimized strategy called the border-based floodfill approach. The key insight here is that any O that cannot be surrounded, and therefore cannot be flipped to X, must be connected to the border of the board. Instead of checking every O, we focus only on the O's located along the border. From these border cells, we perform a DFS or BFS to mark all connected O's as safe, using a temporary symbol like hashtag. After marking the border connected O's, we traverse the board again. Any O not marked as safe is flipped to X, while the temporarily marked hashtag cells are reverted back to O. This method is much more efficient because each cell is processed at most twice, once during the marking phase and once during the flipping phase, resulting in a time complexity of O(m*(n). Another approach worth discussing is the union find, or disjoint set, method. Here, the intuition is to group connected components of O's and track whether they are connected to the border. A dummy node is introduced to represent the border, and any border connected O is unioned with this dummy node. To implement this, we initialize a union find structure and traverse the board, unioning adjacent O's and connecting border O's to the dummy node. After processing all cells, we traverse the board again, flipping any O that is not connected to the dummy node into X. While this approach is efficient, with a time complexity of O(m*(n)alpha(m*(n), where alpha is the inverse Ackermann function, it does come with some trade-offs. Specifically, it requires extra space for the union find structure and is more complex to implement compared to other methods. Among these approaches, we chose the optimized border-based flood-fill strategy because it strikes the right balance between simplicity, efficiency, and clarity. The key observation here is that any O that cannot be captured must be directly or indirectly connected to the border. By focusing solely on these border O's, the approach avoids redundant work and ensures linear time complexity, O(m*(n). Additionally, it's straightforward to implement, with no need for auxiliary data structures like union find, and it's easy to debug. While this method does temporarily modify the board by using symbols like hashtag, this is a minor trade-off since the board is mutable. On the other hand, the union find approach, while viable, introduces extra space complexity and implementation overhead without significant performance gains. For these reasons, the border-based flood-fill method is the most practical and efficient choice. The brute force approach, while conceptually simple, is highly inefficient due to its repeated traversals of the board, making it unsuitable for larger boards. By contrast, the optimized border-based flood-fill strategy delivers the desired results with greater efficiency. Its time complexity is O(m*(n), as each cell is processed at most twice, and its space complexity is O(1), since it operates in place without requiring additional data structures. This makes it a robust and scalable solution for the problem of surrounded regions. This problem challenges us to identify and modify regions of O on a 2D board that are completely surrounded by X. Importantly, any O that touches the border of the board is not considered surrounded, meaning it should remain unchanged. The goal is to flip all surrounded O cells to X while preserving the unflippable ones. To tackle this, we begin by understanding the problem constraints. The board is a 2D grid of size mxn, and a region is defined as a group of connected O cells, connected either horizontally or vertically. A region is surrounded if none of its cells touch the border. The selected approach uses depth-first search, or DFS, to mark all border-connected O cells as unflippable. This ensures that only completely surrounded regions are modified. The steps start with initializing the dimensions of the board, so we know the size of the grid and can traverse it effectively. Then, we focus on the borders of the board, because any O connected to the border is automatically unflippable and should be marked during this traversal. Now, when traversing the borders, we first loop through the top and bottom rows. For each cell in these rows, if the cell contains O, we perform a DFS to explore all connected O cells and mark them as unflippable. Similarly, we loop through the first and last columns and repeat the same process. During the DFS, any border-connected O is temporarily marked with a special character, such as T, to differentiate it from other O cells. This marking ensures we don't accidentally flip these cells later. Once the borders are processed, we move on to traverse the entire board. During this phase, any remaining O cells are part of a surrounded region, so we flip them to X. Meanwhile, any cell marked as T is restored to O, confirming it as unflippable. After completing these steps, the board is modified such that all surrounded regions are flipped to X, and unflippable regions remain as O. This approach leverages the fact that any O connected to the border cannot be surrounded, saving unnecessary computation and ensuring correctness. Additionally, this algorithm is implemented in place, meaning it operates directly on the board without requiring extra space for a separate data structure to track visited cells. The temporary marker T helps achieve this by allowing us to differentiate unflippable O cells from others. In terms of efficiency, the time complexity of the algorithm is O, m*n, as each cell is visited at most once during the marking and flipping phases. The space complexity is also efficient, requiring O, m*n, space in the worst case due to the recursion stack used by DFS. Some key data structures in this solution include the board itself, which is represented as a 2D array for in-place modification, and the DFS stack, which is used to explore connected regions of O cells. It's also important to handle edge cases, such as empty boards, single row or single column boards, and grids where all cells are either O or X. These cases ensure the algorithm is robust and performs correctly under different scenarios. With all these considerations in place, the solution is both efficient and reliable. Finally, the Python implementation of this algorithm begins by checking if the board is empty or invalid. If the board passes this check, we calculate its dimensions and define the DFS function. This function recursively marks connected O cells as T and explores their neighbors in all four directions. We then mark all border O cells and their connected regions by performing DFS on the top, bottom, left, and right borders of the board. Once this marking is complete, we loop through the entire board to flip surrounded O cells to X and restore marked T cells back to O. This ensures that the board is modified appropriately, with all surrounded regions flipped and unflippable cells preserved. The final solution efficiently handles the problem requirements, maintains clarity in its implementation, and achieves the desired output in a single traversal of the board. Here, we start by defining the solve method inside our solution class. This method takes the board as input. Before diving into the logic, we handle an edge case. If the board is empty or contains no rows, we simply return since there's nothing to process. Next, we determine the number of rows and columns in the board, as this will help us navigate through it. We then define a helper function DFS, which stands for depth first search. This function takes a specific cell, represented by its row and column indices, and explores its neighbors recursively. If the current cell is out of bounds or doesn't contain the character O, we stop further exploration. Otherwise, we mark the cell as part of the escape region by changing its value to E, and continue the search in all four cardinal directions, up, down, left, and right. Now, the first step in solving the problem is to identify all O cells that are connected to the borders. These are the cells that cannot be surrounded, as they have a path to the edge of the board. We iterate through the rows and columns along the borders, and whenever we find an O, we call the DFS function to mark all connected O's as part of the escape region. This ensures that we protect any O regions that cannot be flipped. After marking the border connected O's as safe, we move on to the second step. Here, we iterate over every cell in the board to finalize the transformation. If a cell still contains the character O, it means it is completely surrounded by X's and therefore needs to be flipped to X. On the other hand, if a cell was marked as E in the previous step, we revert it back to O since it belongs to the escape region and should remain unchanged. By the end of this process, the board is updated so that all surrounded regions are correctly flipped to X, while the safe regions connected to the borders are restored to O. This completes the solution, ensuring the board meets the problem's requirements. Here, we're starting with the Java implementation of the problem. First, we import the necessary utilities and define the solution class. Inside the class, we have the solve method, which takes a 2D array of characters, board. This array represents the game board. Before proceeding, we perform a basic validation check to ensure the board is not null and has valid dimensions. If it's empty, we return immediately. Next, we initialize the number of rows and columns in the board to use throughout the implementation. We then define a helper class, DFS, which contains the method markEscapeRegion. This is a depth-first search function that marks all O cells connected to the current cell as part of the escape region. If the cell is out of bounds or not an O, the function simply returns to avoid unnecessary processing. Otherwise, it marks the current cell with E to indicate it's part of the escape region and recursively calls itself for all four neighboring cells, top, bottom, left, and right. Finally, we instantiate the DFS class to use its functionality in the upcoming steps. Now, we implement the first major step of the solution. We iterate over all border rows and columns to identify O's that are connected to the boundaries. These are the regions that cannot be surrounded by X and should be marked as safe. For each row, we check the first and last columns, and for each column, we check the first and last rows. If we find an O in any of these positions, we call the mark escape region method from our DFS helper class to mark all connected O's as part of the escape region. This ensures that any O connected to the border is marked with E. After marking the escape regions, we move to the second step. Here, we iterate through all the cells in the board. If we find an O, it means the cell is surrounded by X and should be flipped to X. On the other hand, if we find an E, we revert it back to O because it was marked as part of the escape region earlier. This process ensures that all surrounded regions are converted to X while preserving the regions that are safe. Finally, we conclude the implementation by completing the loop that flips or reverts the cells. At this point, all cells in the board have been processed, and we've successfully solved the problem by modifying the board in place. The solve method doesn't return anything because the changes are directly reflected in the input board. With this, the entire implementation is complete, and the board is now updated such that all O regions surrounded by X are flipped, while the escape regions remain intact as O. In this example, we are given a small 4x4 board. The goal is to identify and capture regions of O's that are completely surrounded by X's. The first step is to visualize the initial board state. Notice the placement of the O's in the middle rows and columns. These are the areas we will evaluate to see if they are surrounded and should be flipped. At this point, the dimensions of the board are determined, 4 rows and 4 columns. Now, we identify and mark any O's that are connected to the borders as safe because these cannot be captured. Starting with the first and last columns, we find no border-connected O in column 0. However, in column 3, there is an O at position 3-1. Using depth-first search, we mark this O as E, indicating it has escaped capture. There are no further connected O's to explore. Next, we check the first and last rows for border-connected O's, but none are found. At this stage, the intermediate board shows the E at 3-1, while all other O's remain unchanged. The next step is to flip all inner O's, those not marked as E, to X. Traversing the board, we convert these inner O's to X, as they are captured by surrounding X's. This leaves us with an intermediate board where only the previously marked E remains. Finally, we revert all E's back to O since they represent regions that escaped capture. The final board reflects the result. All surrounded regions have been captured, while the border-connected O remains intact. In this second example, we are working with a larger 4x4 board where no regions can be captured. Starting with the initial state, we see several O's spanning across rows and columns. The first task is to identify and mark any border-connected O's as safe. Analyzing the first and last columns, we discover border-connected O's at positions 2-0 and 3-1. Using depth-first search, we mark these O's as E and spread through their connections, marking 1-0, 2-1, and 2-2 as well. The intermediate board now shows these escape paths clearly marked, while the remaining O's are untouched. With the border-connected O's marked, we now flip any remaining O's to X, as these represent captured regions. After traversing the board and performing the flips, the intermediate board shows all inner O's converted to X, leaving only the E's intact. Finally, we revert the E's back to O to restore the border-connected regions. The final board demonstrates that no O's were captured in this example, as all the regions either reached the border or were part of the border itself. In the third example, we are given an empty board. Since there are no rows or columns to process, no operations are performed. The board remains empty, and we return it immediately as the final result. This highlights an edge case where the input does not contain any data, and the algorithm handles it gracefully by terminating without additional computation. To analyze the time complexity of the solution, we break it down into 2 main steps, marking the escape regions using DFS and then processing the board to flip characters. First, during the DFS step, the function is called for all O cells connected to the border. In the worst-case scenario, every cell in the board could be part of the escape region. For an mxn board, there are m times n total cells, and each DFS call may involve constant work to check the current cell and its 4 neighbors. As a result, this step has a time complexity of O, m*n, since each cell is visited at most once. Next, in the flipping step, the algorithm scans the entire board to convert O to X and revert E back to O. This also involves iterating over all m times n cells, giving another O, m*n, complexity. When combining these two steps, the overall time complexity for the solution is O, m*n. Now, let's examine the space complexity. This is determined by two factors: the memory used by the DFS recursion stack and the space taken by the input board. For the DFS recursion stack, in the worst-case scenario, the algorithm might explore an entire region of connected O cells. The maximum depth of the recursion stack will then be proportional to the size of the largest connected region. If the entire board is one large region of O cells, the recursion stack could grow to O, m*n. However, in practice, the depth is limited to the size of the largest border-connected region. As for the input board, since the algorithm modifies the board in place, no additional space is needed to store it. Combining these factors, the overall space complexity in the worst case is O, m*n, primarily due to the recursion stack. Let's contrast this optimized approach with a brute force method. A naive solution would involve checking the connectivity of every O cell to the border individually. This means performing a DFS or BFS from each O cell, which would lead to redundant traversals. In the worst case, every DFS could visit all m times n cells, resulting in a time complexity of O, open parenthesis m times n close parenthesis squared. In comparison, the optimized solution avoids redundant work by only performing DFS for O cells connected to the border. Each cell is processed at most once, reducing the overall time complexity to O, m*n, which is optimal. Looking at best, average, and worst cases, the best case occurs when there are no O cells on the board, so no DFS is needed, and the time complexity is O, m*n, for the flipping step. The average case involves some O cells, with DFS limited to border-connected regions, still maintaining O, m*n. The worst case is when all cells are O, requiring DFS to visit every cell, resulting in O, m*n, time complexity and O, m*n, recursion stack space. Finally, let's solidify this with a mathematical justification. The DFS algorithm performs a constant amount of work per cell as it processes the current cell and explores its neighbors. Since each cell is visited no more than once, the total work done by DFS is proportional to the number of cells, which is O, m*n. Similarly, the space complexity is determined by the recursion stack depth, which in the worst case could reach the total number of cells, also leading to O, m*n. This ensures that both the time and space complexities are directly tied to the size of the board, making the solution efficient and scalable for large inputs. In solving the surrounded regions problem, there are several common mistakes to watch out for. One major issue is the incorrect identification of boundary-connected O cells. Remember, any O cell that is connected to the boundary cannot be flipped because these cells form open regions. Flipping them would result in an incorrect solution. Another frequent pitfall is inefficient traversal, where each O cell is checked individually. This can lead to redundant computations, especially in large boards, pushing the time complexity unnecessarily high, even up to O(n)^, in extreme cases. Modifying the board prematurely during a DFS or BFS traversal is another critical error. Changing the state of the cells while still traversing can disrupt the algorithm, causing certain cells to be skipped or revisited incorrectly. Lastly, it's crucial to handle edge cases properly. Examples include boards with no O cells, single row or single column boards, or cases where all boundary cells are O. Ignoring these scenarios can lead to errors like null pointer exceptions, infinite recursion, or incorrect outputs. Overcomplicating the algorithm is another mistake to avoid. Sometimes, candidates introduce unnecessary data structures or overly complex logic, even when simpler approaches like marking visited cells are sufficient. This not only increases space complexity but also makes the code harder to debug. When approaching this problem, it's helpful to recognize that it's a classic graph traversal question involving connected components. Identifying this early can guide you toward the right strategy. A powerful insight is to begin with a boundary-first traversal. By starting at the edges and marking reachable O cells, you can simplify the problem by isolating regions that should remain unchanged. Additionally, you need to carefully weigh space versus time trade-offs. For instance, decide whether you'll modify the board in place or use extra memory to track visited cells based on the constraints. Lastly, during an interview, it's important to communicate your thought process clearly. Explain why you're marking boundary-connected regions and how you plan to handle the remaining cells to ensure the interviewer understands your approach. This problem is closely related to several others on LeetCode, making it a great way to build your understanding of graph traversal. For example, LeetCode 200, number of islands, involves counting connected components of 1, which is conceptually similar. LeetCode 1254, number of closed islands, is another variation where you identify enclosed regions. Of course, there's the original problem here, LeetCode 130, surrounded regions. Lastly, LeetCode 695, max area of island, focuses on finding the largest connected region. Beyond these related problems, there are alternative approaches you can consider. Using DFS is a popular method where you mark all boundary-connected O cells with a temporary marker, then flip the rest. While it's simple to implement, it may cause stack overflow for very large boards. DFS is another good option that avoids stack overflow by using a queue. Although it requires slightly more memory, it's often safer for larger inputs. For a more advanced approach, you can use union find. This treats each cell as a node in a graph and groups boundary-connected O cells into a special set. While it's efficient for disjoint set operations, it's more complex to implement. Another technique to consider is in-place mutation. This involves directly modifying the board during traversal, such as temporarily marking O cells and flipping them back as needed. The main advantage of this approach is that it saves space since you don't need to allocate additional memory for tracking visited cells. However, it comes with its own risks. If the process is not carefully managed, it can lead to errors where the state of the board becomes inconsistent, resulting in incorrect outputs. This approach requires a strong understanding of the algorithm's flow to implement safely and effectively. Thank you for watching. Today, we covered the problem surrounded regions, diving into grid traversal and algorithm optimization. Remember to keep practicing these techniques to strengthen your problem-solving skills. Like, share, and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!